Good afternoon, everyone. In this tutorial, we're going to learn about sampling data. So sampling is a way to pull random values from a population of values. I went ahead and got our usual copy of the MT cars dataset, so we have some sample data to work with. To get started, let's go ahead and pull a sample from the horsepower field. To do so, the function is sample. Then we specify what vector are we pulling a sample from. Then we specify the sample size that we would like to pull. I'm going to go ahead and pull a sample size of 5. When I run that, it's going to pull 5 random values from the horsepower field. If I run it again, it's going to pull 5 random values again. They may be the same, they may be different. It's fully random each time, independently of all the other times. If I want to, I can do something like take the mean of a sample from the horsepower field. And when I do so, instead of seeing the 5 values independently, I'm going to see the mean of those 5 values. And if I do that several times, we'll get a little bit of a different mean each time. If I look at the actual mean of the horsepower field, we'll see it's 146. So you'll notice the means of my samples are often off by a bit from the actual population mean. If we want to approach the population mean, we can increase our sample size. This will get us closer to the actual value. So let's pull a larger sample and take the mean of that. And you'll notice we're a little bit closer. Again, if we repeat this, sometimes it'll be off by quite a bit, but overall we'd expect these values to be a bit closer to the actual population mean. If we increase our sample size again, this time to about half the population, the means we'll see we should expect to be fairly close to the mean of the actual population. This is why people talk about the importance of sample size in different sorts of studies or research projects. The bigger your sample, the more likely that your outputs will reflect the values in the actual population. Let's go ahead and do another sort of fun classic example. Let's go ahead and simulate flipping a coin using the sample function. So the first thing I'm going to do is create my coin, and that's going to be a vector with just 2 values, 1 and 0. So we'll say that 1 represents flipping a heads and 0 represents flipping tails. If I want to simulate flipping the coin, I can pull a sample from that set with size 1. In this case, I flip tails. And if we repeat that, it would be like flipping the coin again and again. If I want to flip the coin more than once, you might think that I could just pull from this dataset more times, but we're actually going to see an error. This is because by default, when we pull a sample, the same value can't be taken more than once. So when we were sampling the horsepower, when this 93 got picked by our sample, it couldn't be chosen again. If there were a different 93, that would be perfectly fine to be chosen, but this given 93, once it's chosen, is no longer valid to be picked again in the same sample. If we want to change that, like in this case for flipping our coin, we can by just adding the argument replace equals true. Now we can flip our coin 5 times without having to do it one by one. If I want to, I can flip the coin as many times as I want as well. When we're doing something like this, one thing you might ask is, well, how many heads did you flip? If I want to see that, all I would have to do is get the sum of this sample. Now, instead of seeing each flip individually, I can see how many heads were flipped in total. This would be the equivalent of handing someone else a coin saying, flip this 10 times and report back to me how many heads you flipped. And we could do that over and over again. If we wanted to, we could even simulate doing this with many, many, many people. In this case, rather than doing it one by one, we might want to use the command replicate. So replicate is going to pull a sample many times. In this case, I want to replicate the script we just ran. I want to sum the sample of flipping my coin 10 times, replace equals true. And we'll replicate that 100 times. So over 100 trials of flipping a coin 10 times, that's how many heads we saw. Let's go ahead and save this vector. We'll just call it coin flips. Oops. And let's go ahead and pull a histogram of these coin flips. And what we see is it's not a perfect normal distribution. Let's go ahead and pull the mean of coin flips. 5.22. So we know that the way we're creating these numbers, the mean should be 5, right? But what we see is roughly a normal distribution with a mean of 5. Again, this is one of those cases where a larger sample size will make your data more accurately reflect the underlying actual values. So let's go ahead and change coin flips. Instead of just 100 people flipping the coin 10 times, we'll make it 10,000. Now if we create that histogram, you'll notice it looks a lot smoother. It looks a lot closer to an actual normal distribution. And if we pull the mean, it's very, very, very close to 5. So these are just some neat things you can do. Some of the other ways you might want to create a data set to do things with. If you want to create a sequence of numbers, you can, if it's just integers in a row, you can do it as simply as like that. That's going to return the numbers 1 to 20 in order. If you want to return some particular sequence, you can use the function seq, that stands for sequence, and that's going to ask you, well, let's refresh. Let's hit F1 here. So to generate a sequence, you say, where do you want it to start, where do you want it to end, and how many do you want it to count by? So in this case, let's start our sequence at 1, end it at 20, and we'll have it count by 2s. So there's all the odd numbers between 1 and 20. Another thing you might want to do is to create random numbers that follow some particular normal distribution. So if I wanted to do that, I'll assign these values to a vector. I'll call it distribution. We use the function rnorm. Rnorm will ask you for 3 things. How many random values do you want? I'll take 100 random values. What do you want the mean to be? Here I'll set the mean to 80. And what do you want the standard deviation to be? I'll pick 8. So this generated, well, let's go ahead and look at it. This generated a whole bunch of values. These are random numbers, 100 of them. They have a mean of 80, and they have a standard deviation of 8. So if I take the mean of that distribution, what would you expect to see? Well, the mean's not exactly 80. That's because this is pulling as if it were pulling from a population with a mean of 80 and a standard deviation of 8. So the mean that we create from our actual sample may vary a little bit. We'll see the same thing with the standard deviation of our sample. It's not quite 8. It's very close. It's 100 values. It's a large enough sample size that it'll reflect fairly closely, but it's off by enough that it's not exactly. So those are just some neat things that we can do to generate sets of numbers that we can use. Just like with our coin flips, as we use the larger sample size, the results we get more closely mirror what we would expect to see. If we increase our sample size here, we'll see the same thing. So if I pull the mean now, it's incredibly close to 80. If I pull the standard deviation now, it's going to be very, very close to 8, right? And if we create a histogram of this distribution, we'll see it's essentially the normal distribution with a mean of 80, which is exactly what we said the population we were pulling from is. So these are some neat things you can do to pull samples from actual data sets, to create samples of random numbers, or to do things like simulating coin flips. You would use a similar process to simulate, I don't know, all sorts of statistics problems, pulling marbles from a bag, pulling people from a population, whatever it might be.